Good afternoon, everyone. Today we'll discuss about thermoelectric effect. As the name indicates, it is about the production of electric current when the temperature difference is maintained. Means the thermoelectric effect is the direct conversion of temperature difference into electric voltage and in turn to the electric current. Or whereas in thermoelectric materials there are free carriers which carry both charge and heat. And if we go to the history, in the 1820s, or if I talk exactly, it was in 1826 when a German scientist named as Thomas Seebeck discovered that if two metals at different temperature were touching could create an electric current. That means it was a thought through which electric current was produced by maintaining the temperature difference of two dissimilar metals, and followed by another scientist from France known as Jean Peltier in 1834 discovered that an electrical current would produce heating or cooling at the junction of two dissimilar metals, and this effect is known as Peltier's effect. And later in 1851 Lord Kelvin discovered that when the current flows through the unequally heated conductor, heat is either evolved or absorbed through the conductor, which is known as Joule's heating effect or Thomson effect. So there are three important effects which are responsible for producing an electric current through the temperature difference. So we'll take them up one by one. First is the Seebeck effect, second one is the Peltier's effect, and third one is the Thomson effect. So let us move to the first effect, which is known as Seebeck effect. See here, there are few appliances which are based on this thermoelectric effect. See here, there are watches from Seiko company which introduces the thermic watches, and there are some home refrigerators. They were existing in 1959 and radio in 1930, and cardiac pacemaker in 1970. So on which this thermoelectric effects were taken into consideration. You can just go through them one by one. So this is Seebeck effect, and thermoelectricity known in physics as Seebeck effect. John Seebeck found that a circuit made from two dissimilar metals with junction at different temperature would deflect a compass magnet. See here, you can see here there are two different metals. One is copper, another is bismuth. They are joined at two junctions. One is kept at cold and another one is kept at hot. And there is a one magnet needle which is connected in between the thermocouple, and it was found that the magnetic needle was showing some deflection. That means naturally there is a production of electric current if your magnet is showing some deflection. And finally he discovered a small current flow and so demonstrated that heat could be converted into electricity. Further, when the junctions of two different metals are maintained at different temperature, the EMF is produced in the circuit, which is known as Seebeck effect. You can see over here there are two different metals which are maintained at two different temperature. One is as T and another one is at higher temperature, that is T plus delta T, which is connected to the some voltmeter or galvanometer. So you can see that this conductor one is maintained at temperature this and another one is maintained at temperature T. Since the junction are maintained at different temperature, the EMF flows across the circuit. I hope now the concept is clear and about what these effects are basically explaining about. So finally, let us come to the Seebeck effect, the phenomena of production of electric current due to the temperature difference between the two junctions of dissimilar metals connected in parallel is called Seebeck or thermoelectric effect. Alright, you can see over here we have two dissimilar kind of metals. They are joined like this, and finally it is connected to a voltmeter which will give you the voltage produced or EMF produced in this kind of circuit. One junction is maintained at hot, another one is maintained at cold junction. So there are few terms. First term, which is known as thermocouple. It is basically a pair of different metals by which a thermoelectric current is produced, which is known as thermocouple. And second one is thermoelectric EMF. If a current is produced in two dissimilar metals joining at different temperature, that means naturally there is an existence of EMF across it. Alright, that means, as we know, that this EMF or current is produced basically because of the difference of temperature maintained across the two junctions. So the EMF produced in such manner is known as thermoelectric EMF, and the resulting current is basically known as thermoelectric current. If we summarize, this effect is called Seebeck effect, and the combination of two metals in such a manner is called thermocouple, and EMF generated in the thermocouple is known as thermo EMF, whereas the current which flows along the closed circuit is called thermoelectric current. Alright, I hope now it is clear that what is the Seebeck effect about. The third term which is very important here is the origin of EMF. See here, when two dissimilar metals are maintained or joined together at same temperature, there is a difference in the electron density in both the metals. You know that. Alright, and the electrons always have tendency to move from higher electron density to the lower electron density. That means production of electric current is there because the potential difference is maintained across the two junctions, but because they are joined together at the same temperature, that means the EMF, or you can see that the potential difference produced across the two junction will have equal and opposite values. So finally, no electric current is produced. Alright, when we maintain or create a variation in the temperature of these two junctions, there is a development of an EMF across the junctions, and which results into the production of electric current. And this is how the origin of this EMF take place. Alright. And next, see here, variation of thermoelectric EMF with temperature. So we'll see that how this thermoelectric EMF is varying while we keep on increasing or decreasing the value of temperature. Alright, and see here, this is the experimental arrangement. We have a thermocouple made up of copper and iron, and there is one galvanometer connected in between, which gives you the deflection, or which shows you that the current is flowing. And you can see there are two junctions. One junction is kept in the oil bath and it is kept at the hot. Alright, there is a burner which will keep on increasing the temperature of this oil bath, and we can measure the temperature with the help of the thermometer immersed in the oil bath here. And second junction is maintained at the cold, that means it is put in the ice tub, you can see here, and the temperature here is 0 degrees Celsius, which is constant always, and this temperature is known as critical temperature. Alright, now see how it actually behaves when we keep on increasing the value of temperature. That means naturally the galvanometer will show you the deflection, and that means the current is increased, or the thermo EMF will go on increasing with increasing the temperature. It will reach to the, see here, there is a plot of thermo EMF with the temperature of hot junction. Alright, that means see here, this is a critical temperature, that means it was at 0 degrees Celsius, and while we keep on increasing the temperature, that means thermo EMF is increasing with the increasing temperature, and there is a one point at which the thermo EMF will have the maximum value, and that temperature is basically known as neutral temperature and is denoted by theta n. Alright, that means maximum value of thermo EMF will exist over here, means we'll have constant value of thermo EMF here. After that, when we go on increasing the value of temperature, this thermo EMF start decreasing till it reaches to the zero. Alright, if we further go on increasing the value of temperature, the thermo EMF again keep on producing, but in the reverse direction. That means this temperature at which the thermo EMF produces production reverses its direction is known as temperature of inversion, which is denoted by theta I. Clear? That means theta n is the neutral temperature which is constant for a given thermocouple, and whereas it is theta I, not Ti. It is the inversion temperature or temperature of inversion beyond which the EMF start increasing in opposite direction. Alright, so here you can see that theta I minus theta n is equal to theta n minus of theta c. Why it is so? It was found that the temperature of inversion is greater than neutral temperature in the same manner as the neutral temperature is greater than as compared to the critical temperature. That means temperature of inversion minus of temperature of temperature neutral temperature is actually equal to the neutral temperature minus of critical temperature. So when we plot a graph, you can see that we'll have the graph in the form of parabolic, and the equation which represent the variation of this thermo EMF with the temperature is denoted by E is equal to alpha theta plus half of beta theta square, whereas E represent the EMF produced. Alright, alpha and beta are constants which are different for different thermocouples, and whereas theta is the temperature of two junctions when the temperature of the cold junction is 0 degrees Celsius. Further, relation between neutral temperature and temperature of inversion. I have already told you the neutral temperature is as greater than the critical temperature as temperature of inversion is greater than the neutral temperature. That means we can present them like this way, or if we take neutral temperature toward this side, it will be 2 theta n is equal to theta I plus theta c. So we can see there that how this neutral temperature is related to the temperature of inversion and the critical temperature. This is the relationship, and generally you get numerical problems on this based on this formula. See here, if you are given with temperature of inversion, you can always calculate the temperature, neutral temperature, because you know that the value of theta c is always 0. Or further, you can also calculate the value of neutral temperature if the temperature of inversion is given, and vice versa. So this was all about the relationship between neutral temperature and the temperature of inversion. Further, it is thermoelectric power or Seebeck coefficient. The differential coefficient of the thermo EMF with respect to the temperature of hot junction keeping cold junction at 0 degrees Celsius is known as thermoelectric power or Seebeck coefficient. You know that what is differential coefficient of thermo EMF? It is denoted by S, which is equal to dd theta of EMF. Alright, this is the differential coefficient. Alright, so see here, we know that when we have a variation of thermo EMF with the temperature, it can be represented by the equation E is equal to alpha theta plus half of beta theta square, whereas alpha and theta are constants, and theta is the temperature of hot junction and cold junction is at 0 degrees Celsius. Calculate the differentiation of this equation with respect to temperature theta, we'll get the thermoelectric power or Seebeck coefficient. It is dd theta of alpha theta plus half of beta theta square. It will be is equal to derivative of this factor and plus derivative of this factor. So we'll get it as alpha d theta over d theta plus half of beta d theta square. You know that how to differentiate basically this equation. So finally we'll get it as alpha plus half beta 2 theta. Or further, 2 and 2 will get cancelled out. Finally, we are left with alpha is equal to, S is equal to alpha plus beta theta. You can see that this equation resembles with the equation of straight line, that is y is equal to mx plus c. That means clearly S varies linearly with theta, and we know that the thermo EMF varies linearly with the temperature. Graph between S and theta will be straight line because it is representing you the equation which is same as that of the equation of straight line. When theta is equal to 0, equation number 1 becomes S is equal to alpha. See here, when temperature theta is equal to 0, S is equal to alpha. Again, S is equal to 0, equation number this is basically equation number 1. This equation number 1 becomes 0 is equal to alpha plus beta theta neutral. You know that what is S? It is the rate of change of EMF with respect to temperature. Why it is taken as 0? See here, what is the maximum value of, where is the maximum value of thermo EMF? It is when the temperature is theta neutral, alright? Because it is constant, when I differentiate this EMF over here, it will give me the 0 values. That means you can see there, I have taken it as 0. It will be alpha plus beta into theta neutral, because at neutral temperature, the derivative of thermo EMF will be 0 because it has the maximum value over here, which is equal to constant. Similarly, you can calculate the value of theta n from here, which is minus of alpha divided by beta. Alright. Now, let us come to the determination of neutral temperature and temperature of inversion in terms of alpha and beta. We know that alpha and beta are the constants, and variation of thermo EMF with temperature difference, theta is represented by this equation, which is EMF is equal to alpha theta plus half of beta theta square. See here, when the temperature is equal to temperature of inversion, thermo EMF is 0. You know that it becomes 0 from the graph and it reverses its direction. That means if we substitute the value of temperature of inversion, this EMF is going to give you 0. See here, it is like this way, and we can solve it like this way, and finally we'll get the value of temperature of inversion is equal to 2 into minus of alpha into beta. This is the calculation of temperature of inversion in terms of alpha and beta. And second case is when the temperature difference is equal to the neutral temperature, EMF is maximum. We know that maximum means constant. If I differentiate it with respect to temperature, that means it is going to give me the 0 value. Alright, that means differentiation of EMF at temperature is equal to neutral temperature will be is equal to 0, which is also known as the Seebeck coefficient or thermoelectric power. Or alpha is equal to, when I differentiate this equation, I'll get it as alpha plus beta into theta is equal to 0. Replace theta by theta n and calculate the value of theta n, which comes out to be minus of alpha upon beta. So let us consider this as equation number 2. Now from equation number 1 and 2, we can also determine the relationship of temperature of inversion and neutral temperature. That means it comes out to be as temperature of inversion is equal to twice of neutral temperature. This was all about the derivation, calculations and understanding of Seebeck effect and the thermoelectric effect. I hope it is now clear that how this effect basically produces the electric current by maintaining the temperature difference across two junctions, and calculations of various terms like thermo EMF, temperature of inversion and neutral temperature. These all are important because the numerical problems are generally asked on this to calculate the value of inversion temperature if neutral is given, and calculate the value of EMF when the neutral temperature or temperature of inversion is given. So I hope this is all understandable now, and this was all for the day. Still, if you are not able to understand anything anywhere, you are most welcome to let me know. Thank you and have a nice day.